Hello everyone! In this video, I'm going to discuss central limit theorem. And for our objectives, the first one is to illustrate the central limit theorem, what is it all about. Second is to define the sampling distribution of the sample mean using the central limit theorem. And the third one, we are going to solve problems involving sampling distribution of the sample mean. So first, let us have a review. So what is the formula to transform a score to its corresponding z-score? If you can recall, that will be z equals the score subtracted by the sample mean divided by the standard deviation. And the other question is, what is the standard deviation of the sampling distribution if the population size is unknown? So we have here the standard deviation of the sampling distribution is equal to the standard deviation of the population divided by the square root of the sample size. So, what is central limit theorem all about? If random samples of size n are taken from a population with a mean mu and standard deviation sigma, then the sampling distribution of the sample mean x bar approaches normal distribution with mean, the sampling mean is equal to the population mean, and standard deviation is equal to the population standard deviation divided by the square root of the sample size. And because of that, we can standardize. So here we have z equals the sample mean minus the population mean all over the population standard deviation divided by the square root of the sample size. It seems that we just replace the denominator by um, square root, or we just replace the denominator by the population standard deviation divided by the square root of the sample size. In computing, or in converting a single score to its corresponding z-score, we just use z equals x minus, or the score minus the sample mean all over the standard deviation. But in this case, we have, or in the denominator here, we have the population standard deviation divided by the square root of the sample size. Another thing is, the central limit theorem tells us that uh, as our sample size increases, our sampling distribution of the sample mean gets nearer and nearer to the normal distribution, or it approaches the normal distribution. And it makes sense. It just tells us that the more sampled we have, the more accurate our distribution will be, or the sample mean that we can get. So we have to take note that the formula z equals x minus sample mean, or score minus the sample mean all over the standard deviation, is for individual score. We use it for individual score. But if we are dealing with sample mean, we must use z equals sample mean minus mu all over the population standard deviation divided by the square root of the sample size. And both of these use the standard normal table. In using the central limit theorem, we also have to take note that if the standard deviation or population standard deviation is unknown, we have to compute the sample standard deviation S. Then we can replace the standard deviation by the or the population standard deviation by the sample standard deviation in the formula, provided that the condition here is that n, or the sample size, should be greater than or equal to 30. In the case that the sample size is less than 30, the formula can still be used. provided that the population is approximately normal and the population standard deviation is unknown. So to give you the first example, we have here the height of pupils in Luna Elementary School has a mean of 121 centimeter with standard deviation of 5 centimeter. So in a case that 50 of them are taken as samples, the question is, what is the probability that their mean height is less than 120 centimeter? So we have here mean, or the sample mean, as 120. This is the population mean, 121 taken from this. The standard deviation is 5. The sample size is 50. And we are asked for the probability that their mean height is less than 120 centimeter. So we have this. This is our formula, and we are going to plug the values to the formula. So we have here x bar, or mean sample mean, as 120, population mean 121, standard deviation as 5, sample or sample size as 50. So if we're going to input this in our calculator, we can obtain negative 1.41 as the value of z. Using the z table, the area below z equals negative 1.41 is 0.0793. We can also conclude that the probability that the mean height of the sample is less than 120 centimeter is 0.0793. We can also rewrite it this way. Probability that z is less than negative 1.41 is 0.0793. And the probability that the mean height is less than 120 centimeter is 0.0793. And that will be all for the first part of our discussion in central limit theorem.